works. Subdivisions of the Grassmannian. Okay, and first there is a well-known Schubert decomposition. Okay, so you can subdivide the Grassmannian, Kn, into n choose k Schubert cells. Let me denote them by omega I. And here I is again going to be same I, capital I as in the previous lecture. So it runs over all k element subsets of numbers from 1 up to n. And these Schubert cells well, there are many ways to define them, but let me define them using the notation that we introduced last time, using Plucker coordinates. So you can define them as the set of all points in the Grassmannian such that I, this index capital I, is the lexicographically minimal base of the Matroid. So I is equal to the lex mean subset J such that Plucker coordinate is not 0. So you look at all non-zero Plucker coordinates. These are exactly all bases of the corresponding Matroids, and you just want to fix the smallest one. Okay, that's not the usual way how the Schubert cells are defined, but it's not hard to show that it's equivalent to classical definition. And I just want to mention that such k-element subsets I can be identified with Young diagrams. So there is a simple bijection between k-element subsets and Young diagrams, lambda, that fit inside k by n rectangle. So lambda belongs to k by n minus k rectangle. There is a simple bijection. I'll leave it for you to figure it out. But so this is k by n minus k rectangle, and you look at the Young diagram inside of this rectangle. So if you know what Young diagram is. Okay, and usually, classically, Schubert cells are usually labeled by Young diagrams. And there are some, it's a very nice decomposition. So some facts about this decomposition is that, well, it's not immediately clear from this definition, but actually it's true. It can be shown that these are really cells. This omega I, it's homeomorphic to an open ball. So they have very simple geometric structure. And this is a CW decomposition. This decomposition gives you a CW complex. And the main reason, well, there are a lot of reasons why people study Schubert decomposition, but one of the applications is that it allows you to describe the cohomology of the Grassmannian. So the cohomology classes, again, I'm not going to define all this cohomology. If you know what it is, then you know what it is. So I'll just mention in some things. So cohomology classes of Schubert cells form linear bases of the cohomology ring of the Grassmannian. Here I need to fix the field, so over complex numbers. So if you look at the Grassmannian over complex numbers, then its cohomology has a linear basis. It has it has dimension n choose k, and it has a nice linear basis given by the Schubert classes. And
the cells have different dimensions, right?
yeah, and they have yeah, of course, right. They have different dimensions. So can you?
Like the omega I.
Yeah, right. So yeah, and the dimension of omega I can be combinatorially expressed in terms of capital I. Well, it's even easier to describe it in terms of lambda. So it's equal to the number of boxes in lambda. So if you label them in a slightly different way by Young diagrams, then the complex dimension of the corresponding Schubert cell is a number of boxes. Okay, so, and they are related to Schur polynomials. And so this decomposition leads to all classical combinatorics of Schubert polynomial, Young tableau, and so on. So if you know this stuff, then I'm not going to tell about this stuff because it will take maybe a whole course to explain it in details. But if you know about Schubert polynomials, Young tableau, and such things, so all these things are kind of follow from this Schubert decomposition. So it's very nice, like little Richardson rule and many other classical things. So that's basically subject of Schubert calculus. And this is, well, actually one of the Hilbert problems was about Schubert calculus. So that's a very classical thing. It was known well before the Matroids were introduced. Okay, so that's nice decomposition. But now there is another decomposition, which is kind of more interesting for us. It's called Matroid stratification. Stratification. Okay, so that's what we briefly mentioned in the end of the previous lecture. So you can subdivide the Grassmannian into much smaller cells than the Schubert, much smaller strata. I shouldn't call them cells because they're also, but much smaller strata than these omega i's into Matroid strata. Let me denote them by SM. They are labeled by Matroids, well, by realizable over your field Matroids. And these Matroid strata, they're just given by all points in the Grassmannian with given Matroid, such that Plucker coordinate is not equal to 0 if and only if I is in Matroid. Okay? So you see, so it's a much finer subdivision, because here we fix only the lexicographical minimal base. Here we want to fix all bases. So here we want to keep all information about linear. So remember these kind of column pictures. So we have a bunch of vectors. You can think about pointing sign as a bunch of vectors. So I want to keep all combinatorial information about linear dependencies between these vectors. Fix all subsets of vectors that form bases in the space. So this is a refinement, obviously, from the definition. It's a refinement of Schubert decomposition. So facts about Matroid. So and actually you can say it's even more precisely. So Matroid stratification is equal to the common refinement of n factorial Schubert decompositions. For all permutations of the coordinates. So let me explain what I mean by this. So this is a theorem that appears in this famous paper of Gelfand, Goreski, McPherson, Serganova. So by the way, this Matroid stratification, sometimes people call it Gelfand-Serganova stratifications. And people call these S sub n, sometimes they call Gelfand-Serganova cells, fine cells, but they're, as I will mention in a moment, they're not really cells. But anyway, so if you hear about Gelfand-Serganova cells, that's the same thing as Matroid strata. So what I mean by saying that it's common refinement of n factorial Schubert decomposition. So suppose we have a Schubert decomposition. That means that you fix lexicographically minimal base of your Matroid. Well, so lexicographical with respect to the usual ordering of the coordinates. So you usually order the ground set, like 1 is less than 2 is less than 3, and so on. Now, if you pick some other ordering of the ground set, say 3 is less than 1 is less than 5 is less than 7, so somehow permute your ground set, and pick the lexicographically minimal base in this permuted ordering, so that will give you another Schubert decomposition. If you do it for all n factorial decompositions, for all n factorial orderings, so basically that means that you fix the whole Matroid. So really, from the way how we define it, like in the classical definition, this requires some work, but from our definition, it's like a really trivial statement, saying that if you know the graphical minimal set with respect to all orderings of the base set, then you basically know the whole Matroid. Okay, so that's nice things about this subdivision, but, well, I don't know if that's a good thing or not thing, but fact is that these Matroid strata, they are not cells. They're very, in general, they're very far from being open balls, like Schubert cells. So they can have very complicated, geometric structure. Okay, so their geometry can be very, very hard. So they are very far from being open balls. So there is actually a result that makes precise statement about their complications. So there is a famous theorem, which is called Munov universality theorem. Oh. Munov universality theorem that tells you, basically tells you that this Matroid strata can be as complicated as any algebraic variety. So they have basically all kind of hard things, that all kind of complication things, some singularities that may appear in the algebraic variety, they can appear for this Matroid strata. Universality. Thank you. So Munov universality theorem, and this already true for, so already true for Matroids of rank k equals to 3. Even Matroids of rank k equals to 3, for the corresponding cells can be as bad as you can imagine. So let me say a few words why this is true. So first of all, so why, let me start with k equals to 2. So what a Matroid of, so what is, so remember, so k equals to 2, in this case, life is not so hard. So basically, we have a two-dimensional plane, and we have a bunch of vectors on the two-dimensional plane. And we look at all possible, like these vectors v1, v2, up to vn. Have a bunch of vectors on the plane, and you see what are the possible linear dependencies between these vectors. And on the plane, that's relatively easy. So on the plane, the only possible thing is that two vectors can be parallel to each other, or a vector can be equal to 0. That's basically the only possibility. So in this case, the structure of possible dependencies is basically very simple. So all vectors break into classes of parallel vectors, and there might be a bunch of vectors which is equal to 0. So that's combinatorial structure of a Matroid strata in this case, and it's not so hard. But for k equals to 3, so remember, for k equals to 3, and I need, oh, okay, here's the eraser. So for k equals to 3, so remember you can represent a Matroid of rank 3 by a collection of points instead of vectors in a three-dimensional space. You can pick a bunch of points on the plane. And so what are the possible dependencies? Now there are more, well, basically, well, 3 points can be on the same line. So that's one dependence. So 2 points can be on top of each other, or a point can be equal to 0. So you have this kind of, I don't know, arrangement, configuration of I don't know. So something like this. Okay, so some configuration of points with fixed combinatorial type of dependencies between them. You say, well, maybe you say points 1, 2, 3 are on the same line. Points 1, 4, 5 on the same line, and so on. So you fix all these linear dependencies, and then you look at all possible ways to represent at all possible arrangements of points with given combinatorial type. That's the structure. That's how Matroid strata looks like in rank 3. And these things can be very complicated. And
what do you mean by different ways to represent? Which ways are the same? Which are different?
okay, so we fix Matroid. So say that points 1, 2, 3 are on the same plane, line, and so on. So and then you look at all possible arrangements of points on the line with given combinatorial with given dependencies, such that 1, 2, and 3 are on the same line, 1, 4, and 5 on the same line, and but 1, 2, and 4 are not on the same line.
What do you mean by different? Which are different, which are the same?
So
Okay.
For example, you take into account that 3 lines meet in a point.
Yeah, 3 lines meet in a point, and so on. So again, so you fix Matroid, fix M, so which is set of all some subset of triple. Well, in this case, k equals to 3, some subset of triples in N. You fix it, and you say, so if 1, 2, and 3 is not in your Matroid, does not belong to this, then these 3 points are on the same line. If 1, 2, and 4 belong to the Matroid, then these 3 points are not on the same line, and so on. So you fix this and just look at all possible arrangements of points on the line with given combinatorial type. So that's basically the structure of a Matroid cell in this case. And the fact that these things can be complicated is actually it's even well known to high school students. So for well, maybe to good high school students, because what high school students like to do, so you know there are like a lot of problems in high school, do such and such things using only a ruler and a compass. So in particular, if you have only a ruler and a compass, you can add numbers and you can multiply numbers. So what does it mean? So you can think about numbers as lengths of intervals, right? You have one interval of length A, another interval of length B. Then of course it's very easy to add A plus B. You just put these two intervals next to each other like A, B, and that will give you A plus B. But also you can multiply these two numbers using high school geometry. So if you want to multiply, you also need to fix your kind of base interval of length 1. So declare that one interval equals to length 1. Then, okay, I think I remember how to do it in high school. So do you know how to multiply numbers? So I think you just need to draw a picture like this. So here you have 1.
I know someone who does. It's called Thales.
Huh?
I know someone who knows how to multiply.
Okay.
It's called Thales.
Okay. Okay. So anyway, so this is your base. You draw the following arrangement of lines. So this you take length of this interval equals to A. Length of this interval equals to B. Then you draw this triangle, and then this should be A times B. Okay. So. Well, what I try to say is that just using, so you can represent multiplication of numbers by some configuration of points with given dependencies between them. And if you know how to add numbers and how to multiply them, you can do more complicated things. You can basically express any algebraic equation. So you can express any polynomial by some kind of arrangement of lines, or even system of algebraic equations. So you can represent any system of algebraic equation by some kind of arrangement. So just kind of iterate this procedure, because there are a lot of technical details, and not figure out how to do it. So, but point is that for any system of algebraic equations, you can draw sufficiently, maybe large arrangement that represents this system of algebraic equations, whose stratum will be the corresponding variety. Okay, so that means that basically Again, there are a lot of technicalities here, and if you want to know like all details, you just need to read the paper of Nelf. But point is that this strata can be very complicated. Okay, now, so let me kind of draw a big picture, what we have so far. So you have this nice and simple, well, Schubert decomposition that leads to all the classical combinatorics of Young tableau. And you know a lot about Schubert decomposition, so it's nice. And you have a much more fine subdivision, this Matroid stratification. Matroid stratification. Which, as we just mentioned, it's wild. It can be very, so it's wild. It can be very complex. Strata can be very complicated. Okay, so this Schubert decomposition is nice. We know a lot about this, but this is kind of doesn't give us a lot of information. It just tells us the lexicographically minimal base. That's a very kind of rough subdivision, if you like. But you can have a very nice control of combinatorics, of what's going on here. On the other hand, ultimately, we would like to understand these arrangements, geometry of this stratification, but that's kind of, in a sense, no hope. There is no hope to solve this problem in generality. Because if you can solve this problem, if you can completely classify combinatorics of Matroid strata, basically you finish algebraic geometry. So then all algebraic geometers will be out of business. So you can just replace them by computers. But, I don't know, luckily, well, I think that's probably not the case. That's probably just impossible to solve completely, explain all combinatorial subtleties of Matroid stratification. So now, so we can ask a question, is there something in between these two cases?
Are these Matroidal cells also strata? Are they also topologically complicated or just algebraically?
Topologically complicated. So they are like, well, so basically closures of this stratum can be any algebraic varieties. So they can very like complicated singularities and so on. So there is no like, I mean, if you can completely classify them and describe them, then you will finish algebraic geometry. Okay, so the question is there something in between? Is there something between these two cases so that we'll get more control of the Matroid? We don't get not just information about lexicographical minimal base, but kind of more subtle information about the Matroid, but on the other hand, which is still solvable, which is still manageable. You can still, you know, combinatorially describe what's going on. Okay, and the answer is that yes, there is kind of the middle, something in between these two cases. There is some stratification, which is called Positroid stratification. Well, so this Positroid stratification, so it more subtle than Schubert decomposition. It contains all combinatorics of Schubert decomposition, all classical combinatorics of Young tableau is contained here as a special case, but also there are a lot of new features, a lot of new phenomena that appear here. It's more kind of rich than Schubert decomposition, but on the other hand, it's still manageable. It's still not as wild as general Matroid stratification. You still can completely describe everything combinatorially. Okay. And so my goal is to tell you about this Positroid stratification. So it's going to form, it has nice features of the Schubert decomposition. It's going to form, these cells will be open balls, they will form CW complex, and so on. But it will have a more rich, more interesting combinatorics. Okay, so so my goal for the rest of this lecture is talk about this Positroid cells. And okay, and this stratification is based on the notion of a totally positive matrix. Well, total positivity. Okay, so the concept of total positivity was, let me just say a little bit of history. So it was introduced in 30s in works of Crane and other people in Schoenberg. Okay, so they introduced a notion of a totally positive matrix. So what is a totally positive matrix? That's a matrix where all minors, all determinants of all submatrices are positive. All minors are greater than 0. Okay, so for example, for 2 by 2 matrices like A, B, C, D, well, of course, I think many of you, or sure all of you know what a positive definite matrix is. Positive definite means that all principal minors are positive. So that means that it's positive definite if the determinant is positive, is AD minus BC is greater than 0. And also, like A and D are greater than 0. A greater than 0 and D is greater than 0. So that's positive definite. But for total positivity, you also require that all other minors are positive. So in this case, you also require that C is greater than 0 and B is greater than 0. Okay, so in this case, it's relatively easy. But in general, so you look at all submatrices of square submatrices of all sizes, and you want these determinants to be positive. And these guys had some practical applications. So they introduced it to solve some practical problems. And it turns out that this concept was become very helpful in many areas of applied and pure mathematics. So it's somehow appeared in various contexts. And one more recent development in this theory of total positivity was done in the 90s.
It was in between a book, right?
Huh?
There was a book of Carling, and who? A special book dedicated.
Yeah. There is, it's kind of fair point. Yeah. And I'm not going to talk about all this history, but there is a huge lot of applications. Yeah, 60s, yeah. But more recently, in the 90s, George Lustig, extended this concept. So extended total positivity to reductive groups. So he gave a Lie theoretic generalization of this. Not only for matrices, he defined only positive, not only matrices, but for any reductive Lie group. He defined the totally positive part of a reductive Lie group. And also, he defined it to generalized flag manifolds. So again, I'm not going to explain what these things are, but there are some things which are called in Lie theory G mod P. He defined totally positive part of these things. And his definition is based on Lie theory. So in order to understand this definition, you don't need to know much except definition of determinant. So in order to understand Lustig's definition, you really need to know Lie theory. You need to take at least one class in Lie theory. So it's kind of Lie theoretic approach. But in particular, so this G mod P, well, Grassmannian is a special case of G mod P. So there is a notion, well, as a very special case of Lustig general theory of total positivity is the positive Grassmannian. And motivation for Lustig was that this totally positive part of G or G mod P is related to so-called canonical basis. So that's a very important basis in representations of Lie groups. Again, I'm not going to talk about. It has a very deep algebraic structure, and this total positivity is related to this. Okay, now we're going to talk about totally positive Grassmannian. And instead of going through like general Lie theoretic approach, I'm going to go back to like original elementary approach in terms of the minors of matrices. So let me define the totally positive Grassmannian in terms of in a very like simple way. Totally positive Grassmannian, so let me define it as a G, denoted by GR Kn greater than 0. That certain subset of the Grassmannian. Now I need to use real numbers. Instead of complex field, I'm going to use real numbers. So it's a certain subset of real Grassmannian. Well, given in like a very, like basically in for totally positive matrix, you look at all maximal minors. For Grassmannian, we don't need to look at, sorry, here we look at all minors of all sizes, but for Grassmannian, we're interested in the maximal minors, the largest, like in k by k minors. So that's the part of the Grassmannian such that all maximal minors, all Plucker coordinates, are greater than 0. Okay, so that's like the most direct, just kind of, if you like, direct analog of the original concept of a totally positive matrix. And we can also define totally non-negative Grassmannian, GR greater than or equal to 0, Kn, by saying that all Plucker coordinates are greater than or equal to 0. That's totally non-negative Grassmannian. And it turns out that's kind of not immediately clear, but requires a little work to prove that actually this total non-negative Grassmannian is the closure of the totally positive, the risky closure of the totally positive Grassmannian. Okay, so in other words, we're looking at all matrices such that all maximal minors are greater than or equal to 0. Well, actually, this object coincides with what Lustig would call totally positive Grassmannian. So this object coincides with the totally positive part of the Grassmannian defined through Lustig approach, but that's a non-trivial fact. That actually requires a some non-trivial lemmas. It's true, but it's not obvious. Okay, and in these lectures, I'm going to use just this elementary, naive way to define totally positive Grassmannian. Okay, so let me give you a few examples. Example. The simplest example is example when k equals to 1. So remember, the Grassmannian is just the projective space. So what is the totally non-negative Grassmannian? 1n. That's the set of all projective, points in the projective plane, like x1 up to xn, such that all xi's are greater than 0. So in this case, the Plucker coordinates are just the coordinates, projective coordinates. So you require that all of them are equal to. Actually, there is a little tiny thing is that, remember I told you that these Plucker coordinates are defined up to simultaneous rescaling. So you can, if you're really careful, you can also ask me, what does it mean that they are positive? Because they are defined up to a constant. So really a more correct way to say it that they are not positive, but all of them have the same sign. So you can make all of them positive simultaneously. That's more correct way to define it. Okay, but what is that geometrically? Geometrically, that set is just homeomorphic to an n-1 dimensional simplex. Okay, so we have, for example, for n equals to 3, we have a projective plane, and inside of this projective plane, we have this kind of positive octant or how you call it, quadrant, octant. Anyway, yeah, I think octant. Right. So this part of the project, that's the totally positive Grassmannian in this case. That's just a triangle. This is GR greater than or equal to 0, 1, 3. And you see that already in this example that it has some kind of combinatorial structure. So it has vertices, it has edges, and so on. So it looks like a polytop. It looks like, so let me put it in parentheses, because it's not really a polytop, it's not really a convex polytop, because these sides are not straight, so it lives in a projective plane, but it looks like a polytop. It has some kind of combinatorial structure. So it looks like a polytop. Okay, and that's how this positive Grassmannian is going to look in general. So it looks like it has some kind of combinatorial structure. It has faces of various dimensions. And these faces give you stratification of the positive Grassmannian. So for example, this triangle is subdivided into 3 vertices, 3 edges, and 1 face. In this case, it's pretty simple, but you can do it in general, and you have this Positroid stratification of the positive Grassmannian. So that's the Positroid stratification. Well, Positroid decomposition of the positive Grassmannian GRKN. Okay, and this decomposition is basically just, so let me define it. So it's just the intersection of the Matroid subdivision with the positive Grassmannian. So the cells are labeled by Matroids as M. Well, let me denote these cells are SM greater than or equal to 0. They are just parts of the Matroid strata inside the positive Grassmannian. So and these are called Positroid cells. So they're SM greater than or equal to 0. They are just Matroid strata intersected with the non-negative Grassmannian. Okay. So in other words, so what we're saying, we fix Matroid and we say that Plucker coordinates, if your subset is in the Matroid, then the Plucker coordinates should be strictly positive. If it's not in the Matroid, then it's 0. So they're not allowed to be negative. So they're either strictly positive or 0, and you fix exactly the positions, the set of Plucker coordinates which are strictly positive. Yeah, very good question, right? So first of all, these are not Matroids. Like in the usual Matroid decomposition, you run over all realizable Matroids over your field, in this case over R. In this case, it will be even smaller class of Matroids. There will be very special Matroids. So for some realizable Matroids, this cell may be empty. So it may have no part in the positive Grassmannian. But there is a class of Matroids for which this cell is non-empty. And that's exactly my next definition. So these Matroids are called Positroids. So definition, I should erase something. Okay. Let me do it like this. Definition, a Matroid is called Positroid if the corresponding cell is non-empty. M is a Positroid if the corresponding, thing is not equal to empty set. So equivalently, Matroid is, can be realized by a matrix with all non-negative maximal minors with all delta I greater than or equal to 0. So if you can realize your matroid by such special matrix, then we call it a positroid. And what positroid means? Positroid is an abbreviation for positive matroid. So this is means that positive matroid. Positroid. Okay. 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 So theorem. So unlike the Matroid subdivision, Matroid stratification, which is geometrically very complicated, the Positroid subdivision is nice. Right, yeah, that's the case. So that's Plucker coordinates are non-zero if and only if I is in your matroid. So, but in this case, that means that it should be strictly positive. So we're not allowed to, so that means that there's zero if it's not in the matroid, and it's strictly positive if it's in matroid.
But just to make sure, we are no longer partitioning the full Grassmannian, right?
Yeah.
Okay,
We're partitioning
the non-negative.
non-negative Grassmannian. But there is a way to extend it to the whole Grassmannian.
Okay.
So even to complex, there is a way to extend the positroid stratification to, you can complexify these cells, and they will give you positroid stratification of the whole complex Grassmannian. But so far, right now, let me walk the positive part of the Grassmannian. Yes? Yes, right. So, yes, so some special positroid cells correspond to Schubert cells. So again, so there is some subtlety here because Schubert cells are defined in the whole Grassmannian. So, but maybe let me say each Schubert cell has a non-trivial intersection with the positive Grassmannian, and this is going to be exactly some positroid cell, some class of positroid cells. So it means that the Schubert decomposition, so that in this sense, this is a refinement of the Schubert decomposition. So if you take, right. So, but so what I'm trying to say that if you look at the Schubert decomposition, just look at the positive part of the Schubert decomposition. That's already have a same combinatorial structure. The cell, the intersection will have the same combinatorial. I mean, all cells will have a non-trivial intersection, and they will be special cases of these positroid cells. Oh, maybe. Well, there are some little details here, but so basically, you can.
If you take the Plucker coordinate,
What?
If you partition the Plucker coordinates to 2, and you say you want this to be non-positive and this to be non-negative, you get something completely different?
Okay. Right. So if you partition, if you say some Plucker coordinates are positive, some Plucker coordinates are negative, some are 0, then it will be. Well, that will be oriented matroid. So they will correspond to oriented matroids. So, well, realizable oriented matroids.
Will it still take the positive part?
No, it will be complete. Well, no, it will not look like a positive. So it will be different in general. So, so this is a kind of very nice, if you like, a very nice piece of the Grassmannian. But some of them will be, so there are some results that some of them will look like a positive Grassmannian. So of course, because if you take the positive Grassmannian and permute columns of the matrix, that will mean that some minors will be strictly positive, some minors will be strictly negative, some minors will be 0. So it means that some of these things that you are talking about will look like positroids. Well, maybe the permuted coordinates. But there will be other which cannot be obtained in this way. Okay, but theorem is each Positroid cell is a cell. So it's homeomorphic to an open ball. And they form CW complex. So they're attached to each other in a nice way, and they form a CW complex. And even more is true that these Positroid cells can be explicitly constructed. There is explicit kind of combinatorial way to construct them, and they can be labeled by nice combinatorial objects, by, for example, by permutations of some kind. So you can completely combinatorially describe the structure of the poset of the Positroid cells, and I probably will do it in the next lecture. But everything can be done very explicitly, like unlike general Matroid strata. So here we can you can parameterize Positroid cells in a nice way, and so on. So everything can be done very explicitly and very combinatorially. But there is one conjecture here. Let me mention just one conjecture is that this is a regular CW complex. So and that's like in particular it means that each so if you take Positroid cell and take the closure of a Positroid cell, the risky closure, then this is going to be isomorphic to a closed ball. Okay? So that's like, for example, you have this feature if you have a polytop. If you take any open face, take its closure, and then you get a closed face. That's obviously homeomorphic to a closed ball. But that's definitely not true for any CW complex. For example, for the Schubert, it's not true for the Schubert decomposition. So Schubert cells, they're open balls, but if you take their closures, may have non-trivial topology. But for the Positroid cells, for the part of Matroid cells inside of the positive Grassmannian, the topology of the closure, well, conjecturally, it's trivial. And so let me say a little bit about history of this conjecture. So originally, so all the story of the Positroids is some kind of analog and generalization of double Brouwer cells. So there was a nice paper of Famin and Zelevinsky about double Brouwer cells, and they made a conjecture that these double Brouwer cells form a regular CW complex, and you get closed balls, the closures of closed balls. So since this kind of story is a generalization of that, it was a very natural to extend Famin-Zelevinsky conjecture here in this setting. And there were many attempts to solve this problem. There is a lot of confirmation for this conjecture. And for example, Lauren Williams did a lot of work towards this conjecture, and she proved many nice theorems. So particularly, she proved that the poset of these cells has all features of a regular CW complex. It's Eulerian, and so on. So there is a lot of confirmation to this conjecture, and there are even more recent results of Patricia Hirsch about, well, about different things, but they might help to solve this problem. Anyway, so there are new recent developments, so maybe this will be proved. So, but as far as I know, it's still an open problem. So it was an open for a while, and at some point there was even a paper on arXiv that appeared that claimed to solve this problem, but then a mistake was found. So, so really it's a very non-trivial, like very evasive. So even though the definitions are very simple, this conjecture is a kind of very non-trivial conjecture. But possibly it will be proved at some point. Okay. Now, let me give you some examples. So maybe I'm going to give you some examples how this Positroid, positive Grassmannian looks like. Okay, and so examples. So, and as I said, k equals to 1 is very simple. In this case, it is just the usual simplex. So in this case, it not just looks like a polytop, it's actually a homomorphic to a very trivial, very simple polytop. Okay, case k equals to 2. This case is still kind of manageable. It's very, can be described combinatorial, but it's already gives you a very non-trivial complex. So let me tell you, so how this positive Grassmannian looks like for k equals to 2. So what does it mean? So you have a R2, you have a plane, and you have a bunch of vectors, v1, v2, and so on, up to vn. Now, what does it mean that these vectors give you a point in the positive Grassmannian? That means that if you put these vectors in a 2 by n matrix, then any 2 by 2 minor is positive. So what does it mean? That for any I less than j, the pair of vectors vi and vj obtain from each other by counterclockwise rotation. So to go from vi to vj, you have to go counterclockwise. So in other words, these vectors in a positive Grassmannian, if they look like I just showed you, they kind of, if you go around the circle in a clockwise direction, they kind of go in the order. Okay? So they are arranged in some nice way. So in particular, this particular picture represents you a point in the top dimensional cell. So all maximal minors are strictly positive. Now, if you want some to get some smaller dimensional cell, that means that you allow some degenerations. You allow some minors to be equal to 0. So that means that you allow some of these vectors to become parallel to each other. So it means that a smaller dimensional cell might look, so a smaller cell, here is an example. So you might get a vector v1, and maybe v2 is parallel to v1. Okay, maybe then you have a v3. Maybe v4 can be even 0. So if it's 0, it's kind of, you don't, well, maybe, I don't know how to denote 0. Like v4 maybe equals to 0. And maybe you have another bunch of parallel vectors, v5, parallel to v6, parallel to v7. So you see, so there is some nice combinatorial structure here. So all numbers are subdivided into, all vectors are subdivided into set of parallel vectors, and this set of parallel vectors form a consecutive interval. So you cannot have v1 parallel to v3, but v2 is something else, is not parallel to them. So if v1 is parallel to v3, then v2 should be also parallel to these vectors. So they form consecutive intervals. So there's some kind of order here is really matter. Okay. Now let me try to even describe more explicitly the whole complex, the whole positive Grassmannian, all possible cells for our main example, for Grassmannian 2,4. So yeah, I think I need more space here. So let me try to describe. Okay, again, it's very simple structure, but again, it's already gives you a very interesting complex. Even in this relatively simple case. Okay, so the top dimensional cell, oh, let me make it a little bit smaller. It is given by a collection of 4 vectors which are not parallel to each other. So you have, well, let me, instead of v1, v2, v4, I'm just going to write 1, 2, 3, 4. So you have vector 1, vector 2, vector 3, and vector 4. So you have all configuration of vectors which are located like this in this order, and they're not parallel to each other. Now, one of the smaller cells below it, there are 4 possibilities. So, for example, you can make 1 to be parallel to 2. So that's one of the cells of codimension 1. So you have v1, which is parallel to v2, so 1, 2, and v3 and v4 are not parallel to them. And similarly, you can make 2 and 3 parallel to each other. And you can make 3 and 4 parallel to each other. Okay, so 1, 2, 3, 4. And there is one more possibility. So do you see what's the other possibility? So you can make 1 and 4 parallel to each other, but now they kind of point in different directions. So one more possibility is looks like this. This is 1, this is 2, this is 3, and the 4 goes like this. It's parallel to 1, but it points in the opposite direction. So these are 4 cells of the top dimension. Okay, now let's see what are further degenerations. So what can we get here is, for example, you can make 3 parallel to 1 and 2. So there is one cell here of codimension. So this cell has dimension 4, by the way. That's the dimension of the whole Grassmannian. These are all 3-dimensional cells. And the next case will be 2-dimensional cell. And the possibility here is so you can make 1, 2, and 3 parallel to each other. So you have a kind of picture like this. 1, 2, and 3 are parallel, and 4 is not. So it's in the closure of this cell and also in the closure of this cell. So another possibility is that you can make, and similarly you can make 2, 3, 4 parallel to each other and so on. Or you can make 2 pairs of parallel vectors. You can make 1 and 2 parallel and 3 and 4 parallel. 1, 2, 3, 4. So you have 2 pairs of parallel vectors. So it's in the closure of this guy and also in the closure of this guy. Okay. And so on. So there are other things like this. Does anybody see another possibility? Another thing that belongs to the closure of this guy. So here you can make one of the vector 1 and 2 to be equal to 0. So you can make, for example, you can make vector 2 to be 0. So you can, there is another cell such that it looks like this 1. I don't know, should I write 2 equals to 0? That's kind of, can already, well, v2 equals to 0. I don't know how to denote a 0 vector on a picture, but we can make,
Like 2 at the origin.
Right, 2 at the origin. Oh, yeah, that's a good idea. So 2 at the origin. 2 is here, 3, 4. So this cell, where 2 is 0, it's in the closure of this guy and in the closure of this guy. So there are actually 2 things in the closure of this. I mean, okay, anyway, so there are 2. This guy is in the closure of these 2 guys, and also this guy is in the closure of these 2 cells. And so on. So there are more possibilities. So just notice that you cannot make one of these vectors to be 0 just in one step, because that will drop dimension by 2. First, you need to make them parallel to each other, and then you can degenerate one of these vectors to 0. Okay. Okay, so there are more cases, and then will be 12 cells of dimension 1. Okay, and there will be 6 vertices, 6 0-dimensional cells. So what are the vertices? Let me explain you how can we see the vertices. They're the most degenerate pictures. So you want to degenerate these things, make as many zeros as possible, but remember that this vector should still span R2. So you cannot make all of them 0. So you cannot just make all of them 0, but so at least 2 of these vectors should form a basis. But everything else can be 0. So the 0-dimensional cells look like this. You have Vi, you have Vj, and everything else is 0. Yeah, all right. K, I shouldn't use K because K equals to 2. So it's, that's the problem. I cannot use ijk. I'm always tempted to use it. Ij, like everything else is 0, right? So, so you have these 2 vectors, and this is, it looks like it's not 0-dimensional because there is some way to pick Vi and Vj, but actually there are some details that I wasn't very careful. So you consider these arrangements modular linear transformations. Because remember, point in a Grassmannian is an arrangement like this modular GLK. So you identify arrangements like this which are obtained by linear transformation. And if you have just a pair of vectors that form a basis, of course, model linear transformations, all of them are equivalent. So this is really just a single point. And of course, there are n choose k, n choose 2 vertices. So in this case, it's C because n choose 2 ways to pick a pair of vectors. Okay. So remember, last time I told you about the hyper-simplex. So last time I said that one combinatorial model that captures some geometry of the Grassmannian is the hyper-simplex. So let me actually talk a little bit about how this structure is related to the hyper-simplex. So last time we said that we have a nice moment map that sends the Grassmannian to the hyper-simplex. And in particular, for this case, the hyper-simplex is the three-dimensional polytop. It's this octahedron. Okay. So that's the octahedron, that's the hyper-simplex. So let us see how this structure that I just tried to describe. Well, I can finish this. If I had a bigger blackboard and more time, I would be able to write down the whole poset of cells, but I don't have enough space on this blackboard. But you can do it. It's an simple exercise. So here we have this kind of poset, this structure of cells. So how is it related to the hyper-simplex? First of all, notice that it has different dimensions. So this is a 4-dimensional object. This is a 3-dimensional object. But also notice that it has exactly the same number of vertices. And actually, the vertices are exactly the same. So the vertices, the torus fixed. So these vertices are exactly the fixed points of the torus. So exactly the same vertices. And exactly the same, with a little work you can show that it has exactly the same edges. So this guy has 12 edges, this guy has 12 edges. So it means that one skeleton of this object is exactly the same as one skeleton of this object. So it has exactly the same vertices, exactly the same edges. So all faces of the hyper-simplex are going to be faces of the positive Grassmannian. But there will be more. There will be 2 additional faces. So what are these 2 additional faces? They correspond to, they're in dimension 2. So in one additional face, which you don't see in this picture, it's this one. Then you have 2 pair of parallel edges. That's going to be a square. So here all faces are triangles. This polytop will have 2 square faces. Let me show you these 2 square faces. So one square face is, well, maybe should I use colors? Yeah, I don't know. I hope I will not make this picture too messy. But one additional face that you get in the positive Grassmannian is this square. Okay? It's supposed to be a square. And the other additional face is this square. So we'll have 2 square that kind of cut the hyper-simplex like this and like this. There will be faces of the positive Grassmannian. Also, positive Grassmannian will have 4 3-dimensional faces. So what are these 3-dimensional faces? You can also see them in this picture. So if you cut this octahedron like this, you break it into 2 pyramids. So these 2 pyramids will be 2 of the 3-dimensional faces. And if you cut it like this, you also get 2 pyramids. So it has 2 square faces, and it has 4 square pyramids. It has 4 additional three-dimensional, well, not 4 additional, but it has 4 square pyramids. So these are these 4 possibilities. So 2 square pyramids like this, and 2 square pyramids which are obtained by cutting the octahedron like this.
What is the symmetry break? The octahedron can be...
Because you cannot make the pair 4, 2, 3, 1.
Yeah, right. So there is a, yeah, very good. So there is a symmetry in the octahedron, a lot of symmetry. Here, this polytop Grassmannian also has a symmetry, but different symmetry. So it doesn't, so there is a special, so really, so maybe I should mark this vector points. This is 1, 1, 0, 0. This is 0, 1, 1, 0. This is 0, 0, 1, 1. And this is 1, 0, 0, 1. So notice that in all vertices that I denoted, they have 2 1s, but they're cyclically consecutive. And there are 2 special vertices where these ones are not cyclically consecutive. And really, for positive Grassmannian, this cyclic order matters. So you have one kind of long diagonal, like vertical diagonal, that plays a special role. So the whole picture is going to be symmetric if you rotate it with respect to this long vertical diagonal. What?
Is the diagonal spelling the complex?
No.
The intersection of the 2 squares?
Yeah, intersection of 2, so they don't intersect.
No, neither the other 2 diagonals.
I mean, they do intersect in the 3-dimensional picture, but in the positive Grassmannian, you have 2 squares, but they don't intersect.
So tell me, this positive part...
Because you cannot really, I mean, this is, if you like, this is a projection of the positive Grassmannian into 3-dimensional space. 3-dimensional space, they intersect, but in 4-dimensional, yeah.
So positive Grassmannian, positive part of the Grassmannian is affine for simplex, right? It is.
Affine for simplex.
Yeah, that's what you said at the very beginning. The positive part of Grassmannian is...
Did I say that? Is it simplex?
Maybe.
No, it's not a simplex. It's, I mean, actually, it's not a polytop in general.
Okay.
It looks like a polytop, but it's not a convex polytop in general. But it's some CW complex, some CW complex, and I'm telling you the structure of this CW complex. So that's the kind of 3-dimensional projection of this picture.
Because you have a 2-dimensional sphere, and you glued a 2 ball from the inside and a 2 ball on the outside.
I guess, that's true. Yeah, right, yeah, yes. If free skeleton, if you remove, yeah, right, so you have 2 balls like this and 2 balls like this, yeah, I guess that is true.
So did you just describe positive part of the Grassmannian?
Yeah, just describe positive part of this 2, 4.
And it's a 3-sphere. That's what you said?
Well, actually, I'm really, well.
Or 3 balls, because there is also this 4-dimensional stuff, right?
Well, it should, well, first of all, should be a ball. That's the conjecture in general, that it's homeomorphic, closure of every cell is homeomorphic to a ball. So it's, that means that the positive Grassmannian is a 4-dimensional ball. That's true. I mean, conjectural, that is true in general. Still an open, I think, still an open conjecture. At least maybe, again, I don't know. There was some recent, Patricia first said that she has some ideas how to approach it. So maybe it's already proved, but as far as I know, it's still an open conjecture. Okay, anyway, so it's an open ball, but it has a, you see, very kind of non-trivial structure. Okay, so I have a few more minutes. And, 20 minutes. Oh, okay. Oh, that's good. I have 20 minutes. So if I have 20 minutes, let me say a little bit about case k equals to 3. Because k equals to 3 is still, so later I'll tell you how to describe the general case combinatorially, but today I'll try to do these examples. So let me describe k equals to 3 case. It's still possible to kind of do it by hands and describe all possibilities for k equals to 3. So remember, so a configuration of vectors in a three-dimensional space is a configuration of points on the plane. So in general, so you have a bunch of points. So point in a Grassmannian GR3n can be represented by a bunch of by n points on the plane. Now, what makes these n points? So you have points like, let me call them v1, also v1 dot dn in R2. Now, if you put this, well, I mean, again, if you put this two-dimensional, sorry, they are three-dimensional points, but they correspond to three-dimensional vectors. If you put these three-dimensional vectors in a 3 by n matrix, you want any 3 by 3 minor to be positive. So what does it mean? That means that for any triple of points, if you pick any three indices, I, j less than I less than j less than L, so you have 3 points, vi, vj, vl, they form a triangle. So this triangle should have a positive orientation. So it should have a clock, maybe positive is counterclockwise orientation. For any triple of points, the triangle should be counterclockwise. So what does it mean? So it means that if you have a bunch of points in a positive Grassmannian 3n, that means that all of them form vertices of a convex n-gon. So for any, so you have n vertices that form convex n-gon. So this is v1, v2, v3, vn. The vertices ordered in the counterclockwise order. And you see this is basically, so if you want to think about this total positivity, so this total positivity is a kind of generalization of convexity. It's a generalization of convex n-gons, and in general. And so that's, if you just have a convex n-gon, that's the top dimensional phase. Now, if you want to find the structure of low dimensional phases, you want to look at all possible degenerations of this n-gon. So, for example, what are possible degenerations? For example, two of the consecutive edges can become parallel to each other, right? So, a more degenerate, smaller dimensional phase may look like this. You have one point, you have another point, and you might have a bunch of points in between them, and you have something like this, and maybe some of these points can even go on top of each other. If you have get two parallel vectors, then points go on top of each other. I don't know, what's the good way to denote 2 points on top of each other? Should I denote them like this? Okay, so or maybe 3 points go on top of each other. I don't know. Or some points can even disappear. They can go to 0. I know. So let me put them in the middle. So you can have something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, maybe 14 becomes 0, 15 is 0, 16, 1. Okay, so that's how low-dimensional phases look like. And again, you see, so there is a very nice combinatorial structure here. So you can combinatorially classify all possibilities. So unlike the case of arbitrary arrangement of points, because if you pick arbitrary arrangement of points, then, as I said, that it can be dependencies between them can be very complicated. If you know that they are totally non-negative, then the structure becomes much more explicit and much more nicer, and can describe all possibilities very explicitly. Yes? Maybe I should call them like this.
Yeah, okay, so you
Yeah.
assume that they're positively.
Yeah, they form a positive. Yeah, there is. Yeah, actually, I'm cheating a little bit here. So that's probably you want to find exactly how I'm cheating. Here, I'm cheating a little bit because so really this is kind of a projective picture. So really, so it's shouldn't be R2, but it should be a projective plane, and here I kind of assume that all vectors point in one direction, and there is a plane, and we pick a plane so that they intersect this plane in the positive direction, but there are also possibilities that they can go in the opposite direction. So somehow, right? So this is what is happening. But really, if you want to be more careful, you should talk about projective plane. So, and even up to projective transformation, in a sense. So really, so this is really not R2, but well, really, what I'm describing here is actually part of the positive Grassmannian. So really, it should be PR2. Okay. And so in the next lecture, I'll try to give you complete combinatorial description of the cells in the general case without cheating. At least, I'm not sure if I'll have enough time to prove things. Okay. But let me tell you one more thing today. So remember, in the first lecture, I told you two things about the hyper-simplex. I said that there are two nice things about the hyper-simplex. One thing is that hyper-simplex is an alcove polytop. It comes with a subdivision into alcoves. Okay, now how this alcove subdivision looks like, say in this case, so this alcove subdivision looks like this. So we have this special diagonal, like this vertical. Should I use different? Oh, let me use this color. Well, actually, this alcove subdivision is exactly a subdivision of the simplex by these two squares that I described here. So if you take this square and this square, they cut the hyper-simplex into 4 simplices. And that's exactly the alcove subdivision. Okay. So, and then they have a theorem. The other nice thing is that you can describe any Matroid polytop as a convex hull of some subset of the vertices of the hyper-simplex, so that all edges, all one-dimensional edges are already edges of the hyper-simplex. Okay, so there are these two facts about structure of the Matroid polytops and the subdivision of the hyper-simplex and this alcove subdivision. So now, in order to get this Positroid structure, in order to understand the Positroid stratification, you just need to put these two things together. So let me explain what I mean. So what I mean is the following. So that's the result that will appear in our joint paper with Thomas Lamb. So with Thomas Lamb, they proved the following result. Oh, use white color. Okay, so M, if you have a subset in n choose k, so it is a positroid, if and only if. So remember, positroids are some special kind of matroids. So if and only if the following two things are true. So first of all, it should be a matroid, right? PM is a Matroid polytop. So the polytop, the convex hull of these points, should contain only edges of the hyper-simplex. And second is that this polytop agrees with the subdivision into alcove polytops. So that means into alcoves. So it means that PM is an alcoved polytop. That means that it's a union of these alcoves like this. So it kind of agrees, intersect nicely with alcove subdivision. So let me give you two examples. So for example, one positroid. So if you look at this picture again, this example, 2, 4. Okay. So again, this alcove subdivision here, you just need to cut this octahedron by this plane like this that passes through this square and through this square. and you want to take some union of the alcoves so that all edges are already in this picture. So one example is, for example, you can take everything except, say, everything except this vertex below. So for example, if you take this polytop, no. Okay, well, this is supposed to be a square actually. Somehow it's not exactly a square because, let me make it more precisely. So this is, okay. So you took everything except this point, 1, 0, 0, 1, and you see that you get this square pyramid. That's a positroid. It's a union of two alcoves, or a union of two simplices, and it doesn't have any extra edges, which are not shown in this picture. But for example, so this square pyramid is a positroid, but for example, if you take square pyramid like the top part of the hypersimplex, if you take this square pyramid, it's not a positroid. Well, it's a matroid. We don't have any extra edges, but it's not a union of alcoves, because alcoves kind of, I mean, it only contains half of alcoves. Doesn't agree, so it's not a positroid. And so let me explain why this is a positroid and this is not a positroid from using a Plucker relation. So remember, we have a Plucker relation. So kind of try to give you some feeling why this has to be true. So we have this Plucker relation, delta 1, 3, delta 2, 4 equals to delta 1, 2, delta 3, 4 plus delta 1, 4, delta 2, 3. Right? So we have this Plucker relation. And if we are in the non-negative Grassmannian, we know that all these deltas should be non-negative. They cannot be negative. They're either strictly positive or 0. Now, so what we did here, so we removed just one vertex. So this vertex corresponds to subset 2, 3. So the vertex that we removed here, so we just set delta 2, 3 to 0, but you want, sorry, delta, no, not 2, 3. It's 2, 4. Right? You set delta 2, 4 to 0. Here delta to 4 becomes 0, but everything else is strictly positive. Everything else is still here, and that's not allowed, because if this delta to 4 is 0, then you have 0 in the left-hand side, and in the right-hand side you have two positive terms. So 0 cannot be equal to sum of two positive terms. So we're not allowed to set just this guy to 0. Okay? We get a contradiction. But here in this picture, you set delta 1, 4 to 0. So you removed this vertex. But also here, delta 1, 4 equals to 0. So which is OK. So you can set delta 1, 4 to 0. And you can still satisfy this relation. So you have a positive equals to something positive plus 0. So that's allowed. So that means that this is a positroid, but this is not. So and you see, so there is some... as you see in all these examples, the other thing that I will mention, and I'll try to explain in more details next time, if you look at all these examples, and also look at this example here, so there is some kind of cyclic ordering plays a very important role here. So all these vertices are kind of naturally arranged in a circle. So 1, 2, 3, 4, 5, and 1. And similarly here, you see there is a, like, one special diagonal in this octahedron, so where the ones are not cyclically consecutive, but like in this part, so you can kind of rotate the whole picture with respect to this special diagonal. So there is a cyclic symmetry. So in general, the cyclic symmetry of order n acts on the positive part of the Grassmannian. So in all combinatorial pictures that we'll get, hopefully we'll get in the next lecture, we'll have this cyclic symmetry. Okay, so I think I can finish.